Euclid's theorem, the theorem where he shows that there exist infinitely many prime numbers, is my favorite theorem in all of mathematics, and the proof itself is beautiful because the theorem and the proof have everything you would want in a theorem. First of all, the theorem deals with perhaps the most fundamental of all objects in all of mathematics, which is the prime numbers. And the theorem itself shows that there exist infinitely many numbers that are prime, which is in itself an accomplishment, because when you define a mathematical object to prove that there exist infinitely many of such interesting objects, sometimes it's very difficult. Moreover, the proof, which you can see here in its original Greek form, it's constructive in that he shows that if you give him a set of primes, he can tell you how to build a new prime that is not in that set. Now, this is ancient mathematics, so what he actually does in his proof is that if you give him 3 primes, he will construct a 4th prime that is not one of those 3. And finally, the fact that this proof that appeared in Proposition 20, Book 9 of his books, The Elements, some 2,300 years ago, is still the most beautiful proof of the infinitude of the primes, and that it's still so elegant and so interesting, it just boggles my mind. So let's go over a modern treatment of his proof. Our method of proof is that of Euclid. We're going to prove that there are more prime numbers than any finite quantity. So what that means is that we're going to start with an arbitrary set of n primes, and then we're going to find that there is one more prime, that there is at least one more prime that it was not in that set, and therefore, since that was some arbitrary set of primes, and we can show that there's always one more, that will show that there must be infinitely many of them. So that is exactly what we're doing here. Start with primes p1, p2 through pn, some arbitrary set of n primes, and suppose those are given in some increasing order. And then we're going to define a capital N that is going to be the number that is given by the product of all those primes plus 1. Now, the number n has its own prime factorization. So in particular, it has at least one prime factor. Let's call that prime factor q. So n is q times m for some other integer, some positive integer m. Now, I claim that the prime q that divides n is, in fact, a new prime. Because if it was one of the old primes, if it was one of the p1 through pn, so pi for some I, then I can do the following. Remember that n is equal to the product of those primes plus 1. So if I solve for 1, then 1 is equal to n minus the product of the primes p1 through pn. Now, n is q times m, and pi is q, so I get this expression, and then I can factor a common factor of q out of this. So 1 is q times m minus this product of primes, but m minus that product of primes is some other integer, and that means we have a contradiction. We have arrived at a contradiction because we have factored 1 as a prime number q times some other integer, which is, of course, nonsense. And that means that q cannot be one of the primes p1 through pn. Therefore, q is not in the original set p1 through pn, and therefore there is at least n plus 1 primes when we had started from n primes, and this means that there are more primes than any finite quantity, and therefore there are infinitely many prime numbers. It's just so beautiful. And again, the most beautiful part of this is that it does work. You start with the prime 2, 2 plus 1 is 3, is a new prime. 2 times 3 plus 1, that's 7, and it's divisible by new primes. For example, 7. 2 times 3 times 5 plus 1, that is divisible by a new prime, 31. 2 times 3 times 5 times 7 times 11 times 13 plus 1, that is divisible by new primes, 59 and 509, those are new primes. The Euclid's proof does not imply that the product of the first n primes plus 1 will be prime, but it will be divisible by primes that were not in our original list.